The next lesson is 6.3 on other rates of change. So the last lesson we talked about rates of change when it was a speed. And this is just to let you know that not every graph showing a rate has to show the rate of speed. Sometimes a rate could be something like how much it is to buy a hamburger at the fair. If it's $2.50 per hamburger, that could be on a graph. It doesn't need to be a speed. So the graph shows the average fuel efficiency for an older sport utility vehicle and a new smart car. So somebody who drives an SUV as compared to somebody who drives a newer smart car, you can kind of imagine that this fuel efficiency would be a lot higher for a smart car because they don't use much gas. This graph, just when we examine it, I want you to notice that the two different lines don't have the same steepness. So the SUV line is not as steep as the smart car line. And what that means, again, we're looking at kilometers per liter. So the distance driven and the volume of fuel used, this is kilometers per liter. So the smart car can go a higher number of kilometers per liter. And the SUV, because it's down lower, it goes a lower distance for every liter of fuel used. So let's look at the first question. The first question is to ask you about the rate, and that's what we were talking about with the last lesson. If we think about the rate for each, the rate is going to tell us kilometers per liter. Remember, a unit rate is kilometers per 1 liter. We want to know how much per 1 liter. If we want to look at the graph, I know it doesn't say a whole lot over here. There aren't a lot of values given. Some of these points aren't great points. If you look, they're not on nice corners of squares. If we look at the smart car, what I would like to use are the values that I'm given. They actually tell you that this ordered pair right there is 5,120, and the ordered pair up here at the top right there is 15,360. So those are two ordered pairs that you're given. So why don't we use those to figure out the rate? First of all, rate we learned before is rise over run. Vertically is the rise, horizontally is the run. We want to know rise over run. So what that means for these two ordered pairs, that I want to know how the change from there to there, I want to know how tall that is. That's the rise. And then I want to know the run and how wide it is from the ordered pair that starts at 5 down here up to 15 down here. So the rise, what I do know from my graph is that this is 360. So I know it doesn't really show it over here, and we could kind of guess, but it tells me that's 360. That's 360 right there. And down low is 120. So if I follow that ordered pair across, that's 120. And I want to use the values that I'm given. So the difference between 360 and 120 is 240. I would take 360 and subtract 120, and that gives me 240. Okay, that's my rise. My run goes from 5 up to 15. So my run, 15 minus 5 is 10. So rise over run is 240 over 10. Determine the rate of change for the smart car. So my rate is rise over run. And I said that was 360 minus 120 over 15 minus 5. It's the difference between the vertical numbers and then the difference between the horizontal numbers. And I get 240 over 10, which is equal to 24. Okay, and then you have to take a second and think about what that means. 24 kilometers per liter. So the smart car goes 24 kilometers for every liter of gas, and that is the unit rate, or the rate of change of the graph. That represents how steep the graph is. When we look back up at the SUV was the purple line that was down lower. What I want you to know right away is that the rate of change for the SUV shouldn't be 24. So this is that slope. 24 is the slope of the smart car, the rate for the smart car. This is obviously going to be lower. It's going to be 15 or 10 or something like that. We could actually figure out the rate as well for the SUV. So again, when you look for ordered pairs, I hope you know what I mean, that some of these ordered pairs don't really look that good. I don't really know what values they are. If I, for example, wanted to guess what this ordered pair is right there, I would have to guess. I'd come across here and I'd kind of have to estimate. So when we're asked such a specific question, we don't want to have to guess. So what I'm going to use are the ordered pairs that I'm given. There's a change from 90 up to 180, and also a change from 10 up to 20. And that is your rise over run. This is the rise, the second value is the rise, and this is the run. Okay, the vertical numbers are second, that's rise. The horizontal numbers are first, and that's the run. So the rise is how far is it to go from 90 up to 180? So 90 up to 180, that's a difference of 90. The rate of change, so the rate equals the rise over the run, and that's a change of 180 minus 90. That's 90, right? That's the difference. The run, if you remember, went from 20 to 10. So 20 minus 10, that's a change of 10. So the rate of change for the SUV is 90 divided by 10. If you divide, you get 9. And I want you to realize that that's just like the last lesson that we did. We have a rate here. The 9 represents 9 kilometers per liter. And that's how many kilometers you can travel on 1 liter for the SUV. So obviously you can go a lot further in the smart car than you can in the SUV on 1 liter of gas. The more efficient car has a greater rate of change and a steeper line on the graph. It travels farther for each liter used. So the steepness of the lines has to do with the rate. Last question here on the bottom. The smart car's gas tank holds 33 liters of fuel. So when you fill up the gas tank at the gas station for the smart car, it doesn't have a very big tank. But I mean, you can go quite far because it's so efficient. The SUV's gas tank holds 80 liters, right? It holds a lot of gas because it's going to use a lot of gas. Determine how far each vehicle could travel on a full tank of gas. For the smart car, if you remember, it travels 24 kilometers in 1 liter. I'm going to use a ratio. I'm going to set it up as if it travels 24 kilometers on 1 liter, how far would it travel on 33 liters? This is a good ratio question, kind of a review. I might set it up like that. If it's 24 and 1, how many, so I use an X because I don't know how many kilometers would it go with 33 liters? So in order to solve this, I don't know if you remember, but when we have a ratio like this, we can cross multiply. So just a little review. That's a good time to review ratios. So 1 times X is just X, and then 24 times 33 is 792. So that means the smart car can travel 792 kilometers on 1 tank of gas. Then if we do the same thing for the SUV, remember it was 9. It goes 9 kilometers in 1 liter. But if we fill the gas tank, that's 80 liters. So liters go on the bottom. And if we have an X in the numerator, that means we don't know how many kilometers you could go. So what we're going to do is just cross multiply again. So X times 1 is X. 9 times 80 is 720. This should have said kilometers on 1 tank of gas. 720 kilometers on 1 tank of gas. So you fill up each vehicle, and if it's a fill up, if it's actually full of gas, then they'd go about the same distance. So you wouldn't have to stop more often or anything with the SUV. But think about that as far as gas goes. Gas is so expensive right now. Imagine filling up 80 liters compared to 33 liters, right? So this one had 33 liters to fill it. This one had 80 liters to fill it. It's going to cost you, way over 2 times as much to drive the SUV. So that is why you can go as far on a full tank of gas, but the SUV's gas tank is way bigger. Just to finish up here, example 1 on the back, determine each rate of change. So what I need to know is rise over run. And this time we're not given the ordered pairs, but they're much more clear on this graph. So you just have to pick 2 ordered pairs. It doesn't matter which ones you pick. So for example, I could pick those 2. And if I figure out the rise over the run, a lot of students will tell me that's 2 over 2 because it's 2 squares high and 2 squares across. But what you have to figure out is what the squares are worth. Up the side here, it looks like we're counting by 15, 30, 45, 60. So 2 squares is actually from 60 to 30, which is a change of 30. Not 2 squares, 30. It's actually worth 30 kilometers. So that's the rise, and the run from here to here, these look like they're each valued as 1. 1, 2, 3, 4, 5. So that really is 2. So our rise over run, our rate is 30 over 2, which is 15 kilometers per liter. I know it's kilometers per liter because I look at the information that I'm given on the graph. If somebody else had chosen 2 different points, let's say here and here, just to show you. The rise here goes from 60 up to 150, which is a change of 90. So the rise is 90. And from 4 up to 10, that's a change of 6. So we would do 90 over 6. If we take 90 and divide it by 6, we also get 15. So it doesn't matter, kilometers per liter. It doesn't matter which 2 ordered pairs you pick. Often the numbers would be smaller if you pick 2 points that are closer together. So let's just look at the rate here. This is catering costs for dinner guests. So how much it is per person, the cost per guest. Cost per guest. So look at that ordered pair. That is not good. I would definitely have to estimate that number. If you don't know, look for the ordered pairs that do make sense. Like that is a good ordered pair. It's right on the corner of a square. So if I do rise over run for this graph, I can also go down to 0. So my rise, I know for sure that that's 500. It's 500 tall, and the run is 20. So 500 divided by 20 is $20. So right here, our rate is 500 divided by 20, and I get 25. So I want you to always ask yourself what that means. I got 25. That's $25 per guest. You can also imagine if it was $30 per guest, the line would be more steep. If it was only $15 per guest, the line would not be as steep, right? The rate is determining how steep the lines are. Example 2, the graph shows how the height of a small plane changes with time. This one's a little different because the line is going down. What that tells me is height per minute. It tells me that the height of the plane is actually going down. The plane is becoming closer to the ground. So what is the plane's initial height? Okay, the graph tells you that. If you look where the line starts, right there, the initial height must be 1,800 meters. Determine the rate of change. Okay. The difference when the line is going down is that our rate of change is going to be negative. It's going to be a negative number because the rate is decreasing. So if we want to pick some nice points, let's use the 1,800. I don't like that one because it's not in the corner, but I like this one. Okay, then it says determine the rate of change. So what I want you to notice on the graph is from 1,800 down to 1,500, that's a change of 300. And for run, so that was the rise, that's the vertical number. The run goes from 0 up to 2. When we take 300 and divide it by 2, we get 150. But one thing we have to do to this answer is we have to make it negative. What this rate tells us about the plane's flight is that the plane's height is dropping 150 meters every minute.